Good morning everyone. Today I'll be presenting a Python program that I developed which performs pure decomposition using the Gram-Schmidt orthogonalization method. This is a core concept in numerical linear algebra, and implementing it from scratch gives us much deeper understanding of what's actually happening under the hood when we decompose a matrix. Now let's start with the bigger picture. What is pure decomposition? In a way of breaking down any given matrix A into the product of two special matrices called Q and R. Q is what we call an orthogonal matrix. What that means is that all its columns are perpendicular to each other and each column has a length of exactly 1. We call these unit vectors R, on the other hand, is an upper triangular matrix, meaning all the values below the diagonals are 0. Now why do we care? Pure decomposition shows up everywhere in applied mathematics and computer science. From solving system of linear equations to least square regressions to computing eigenvalues to training machine learning models. It's one of those foundation tools that powers a lot of technology we use today. Now looking at the code, we can begin by importing the OS module and setting an environment variable called open_class underscore num threads to 1. This is small but an important step which prevents NumPy underlying math library from spawning multiple threads, which can sometimes cause unaccepted behavior in certain environments. We can then import NumPy, which is Python's go-to library for numerical computation, giving us an efficient array operation and a mathematical function. Inside the function, the heart of the program is the function pure decomposition, which takes matrix A as its input. The first thing we do is read the shape of A, extracting n the number of rows and m the number of columns. We then initialize two empty matrices of size n by n, one called U to hold our intermediate working vectors and other called Q, which will eventually become our final orthogonal matrix. Now we get to the most important part, the Gram-Schmidt orthogonalization process. This is the algorithm that actually constructs our Q matrices and works column by column. For the very first column, we simply copy it directly from matrix A into U and then normalize, meaning we divide by its own magnitude or length to produce a unit vector. This becomes the first column of Q. For every column after that, we do something more involved. We again start by copying the corresponding column from A, but then we loop through all the Q columns. We already computed and subtract the projection of the current column onto each of those directions. What this does is systematically removes any overlap, any shared direction between the current vector and the ones we have already processed. The result is a vector that is completely perpendicular or orthogonal to all previous Q columns. We then normalize this new vector and store it as a new column of Q. This process repeats itself every column until Q has been filled. At that point, we have fully orthogonal matrix where every column is a unit vector and no two columns share any direction overlap. Now for the R matrix, with Q fully constructed, we move on to computing R. Since R is an upper triangular matrix, we only need to fill in values along and above the diagonal. Everything below stays 0. Each entry of R is computed as a dot product between a column of the original matrix A and the column of Q. Geometrically, this is measuring how much of each original direction is captured by each orthogonal basis vector. Together, Q and R preserve all the information of original matrix A that is expressed in a cleaner, more structured form. At the bottom of the program, we take user's input using Python eval function, which allows the user to type in matrices as a nested list. This is then converted into a NumPy array and passed on to our function. The program then prints both the computed Q matrix and the R matrix clearly to the console. So in just a few lines of code, we have gone from raw matrix into a full QR decomposition, computed entirely from first principle. To summarize this program, implements the Gram-Schmidt method to decompose a matrix A into orthogonal matrix Q and an upper triangular matrix R such that A equals Q multiplied by R. It demonstrates a clean, readable implementation of a powerful mathematical concept using Python and NumPy. I hope this gave a clear picture of both what the code does and the mathematician driving it. Thank you for listening and yeah.